So hi, welcome to this podcast. Today is a very special episode. We're actually recording from Basel. We're at the US Switzerland Quantum Symposium. I took the chance to talk with quantum physicist Holmes. Holmes is a researcher at the University of Lausanne in Switzerland. I don't know if it's pronounced that way, but in Switzerland. She works on really cool topics in like quantum thermodynamics, a lot of things quantum, but especially quantum machine learning, which is a topic that I'm very interested in. It's very fascinating. Welcome. Hi, how are you? First of all, thank you for accepting.
Oh, it's cool. Thanks for inviting me.
Okay, yeah, I know quantum conferences are very exciting, but they're also very tiring. So I hope you're okay. Okay, okay, nice.
I'm lucky. I didn't have to travel far. Unlike the Americans who are really jet lagged with 2 days in Europe.
Okay. Okay, so if it's okay for you, I want to start by your talk. You just gave a really cool talk about the limitations and the power of quantum computing. You talk about some of the current problems, how to fix, how to deal with these problems. So, first of all, if you could tell us about what are the limitations of quantum computers, what are the problems that are in a very general way, for someone who doesn't understand that much or doesn't know much about the subject.
So you mean limitations of near-term devices or limitations of quantum computers full stop?
I guess I've meant it more like in the fact like there are, so I will guess in near-term devices or devices now, not like theoretical, but more like a yes.
Yeah, near-term devices. I mean, people that they've improved dramatically in recent years. So you can now run over the cloud. You can run quantum algorithms on what's the biggest device you have access to over the cloud? I mean, okay, easily through IBM you can get devices that are of the order of 20 qubits. Anyone, I think, can basically set up an account and run those. So 20 qubits, it's non-trivial, but it's not massive. So it's far too small to run things like Shor's algorithm that in the media is always touted as the sort of holy grail of quantum computing, being able to factorize large prime numbers and crack RSA. So, I mean, you're looking at millions. I think the last time I read an estimate, it was you needed 2 million physical qubits to factorize 2048 bits. Again, I might be talking bullshit now, obviously, I don't have any notes in front of me,
Okay.
but it's roughly that order of magnitude. So 2 million, 20 million. You're
Okay.
talking millions. We're talking about many orders of magnitude more than the qubits that we have right now. Right now, we have something like 20 qubits. Google, IBM have these bigger devices. We're now looking at 100 qubits, but the average person doesn't have access to them. So we're looking at small-ish devices, way smaller, many, many orders of magnitude smaller than devices needed to require to run these fault-tolerant algorithms. And also these devices are noisy, so they're prone to errors. You try and run a particular algorithm, and it just doesn't run quite the gate that you're after. There are sort of small angle errors. The states decohere. You have errors build up, and it just means you can't run the algorithms that you want to run.
Okay, I see. And I love how you have this approach in the sense that one could easily complain and say, "Oh, too bad we don't have the perfect quantum computers." But I think you have like a quite a optimistic approach, or like a very approach. Okay, we have these faulty devices, these devices that have errors. So okay, one thing that I really like about your talk is how you talk about, okay, we have this, let's see what we can do with this. Maybe after we'll have the perfect quantum computer. But I think a lot of your work is to see what we can do with these faulty devices, right?
Yeah, correct. So, I mean, there are many things you can do right now. I mean, there are lots of people working on different things. There are people working in the lab trying to improve these devices. They're trying to get error rates down. They're trying to make devices bigger, to scale them. And they're trying to do early work on error correction to basically correct errors as and when they arise. And that's really important work.
Mm-hmm.
There's also work for theorists trying to make, so this was James Witten's talk, trying to make these error correction codes better, simpler, more efficient. So there's lots of work in trying to basically help us get towards the fault-tolerant era quicker. But despite all that hard work, we're still a way off. Like, we're still, for the next, and I don't know, it's very hard to put a timescale on these things, but certainly for the next couple of years, maybe longer than that, we're going to have these small, noisy devices to handle. We may have them for, I don't know, half a decade. Let's see if we can do anything interesting with them.
Okay.
So that's, what I work on.
Okay, I see. And a lot of your work involves sort of the mix of quantum techniques, so to say it, but also like you think about a lot of in machine learning. A lot of your work has to do with machine learning. And maybe for people who are not that familiar, I mean, I think everyone has heard the word machine learning, but like it does feel like magic, but I don't think it's magic. Like obviously there's a clear mathematical formulas behind it. So maybe in a general way, if you could talk about what is machine learning and what is this about, like maybe in the general idea, maybe about maybe neural networks, for example, or I don't know, your general vision about the subject. I know it's very vast, so
that's a very, very broad question. A lot of what I work on is a particular corner of quantum machine learning. And that is through hybrid variational algorithms. And that encapsulates some methods that would be seen as quantum machine learning and also some methods that would not be seen as quantum machine learning. But the core idea to that framework is that you have some quantum cost function. So the idea here is, say you've got there's two different ways of coming at it. One way of thinking about it is, say you have a noisy quantum computer and you want to try and make the most out of it. Well, one way you might try and make the most out of it is by using it as little as possible. So just picking a small component of an algorithm to run on the quantum computer and then offloading a lot of the hard work to be done classically. So that's one way of noting variational quantum algorithms.
Okay.
And the idea then is you just pick a cost function. So you pick a cost function that is hard to compute classically, but easy to compute, or relatively easy to compute quantum mechanically. You measure that cost, so it's a loss measure. It's some feature that you care about that encodes some kind of optimization problem. You measure that on your quantum computer, and then classically, you try and optimize it. So the idea is that you've offloaded a lot of the hard work to the classical computer because the classical computer is doing the optimization. Another way of thinking about it is so many problems we have in life are optimization problems. So, for example, all the stuff that trying to figure out I don't know whether people do this here, but back in the UK, I used to get Tesco's delivering my groceries.
Okay.
So I had a big supermarket that delivered my groceries. And then you got to try and figure out, you've got all the places that need their groceries delivered one evening, and you've got to try and figure out the optimum route in order to get around them. So you can play around with different ways of ordering deliveries to try and minimize the amount of time spent on delivery, to try and make sure everyone gets their dinner the quickest. So that's an optimization problem. And the cost there would be time spent to do the deliveries. And the optimization would be to try and figure out different arrangements, try different arrangements, and find out which arrangement, which order of the different houses minimize that cost. So that's one optimization problem. A different optimization problem, classic one that's more interesting for science, is, for example, finding ground states, trying to find the ground states of a molecule or a particular material. And then your optimization problem is you've got some state, you can compute its energy, and you want to try and minimize that energy. So then by basically computing an estimate of a state's energy on a quantum computer, and then minimizing that state's energy, you can try and find the state with the lowest energy, which is the ground state. So lots of things can be formulated as optimization problems, and a nice feature of that is then perhaps you can do the optimization classically and just measure the cost quantum mechanically, and that's offloading a lot of the hard work from the quantum computer onto a classical computer. So all the optimization classically.
Okay, I see. And I guess, finding this optimization, I guess in some cases it could be easy. Maybe in some cases it will not be so easy to optimize this function or this answer or whatever you want to try to minimize the cost function. Yeah. So maybe, I don't know, you want to speak about is there a particular physical scenarios where it's easier or where is it harder, or why is there a fundamental reason that makes it difficult or easy? I don't know.
Yeah, no. So we say, it's going to be great. Let's just measure this cost function on the quantum computer and then do the optimization classically. And we sort of claim the optimization classically, the hope is going to be easy. And as you say, it's absolutely not. Optimization classically can actually be really, really hard. And one thing that matters is the cost landscape. So if you're trying to minimize this cost, what you need to do is you often employ sort of optimization methods to do it, something like gradient descent. So thinking back to the example of trying to find the optimum order for doing your Tesco's delivery, if lots of the routes take about the same time and changing things around doesn't make a huge difference, but then there is a sort of completely different configuration where suddenly you change everything and that makes the time a lot lower, that's going to be harder to find. So if all of the configurations have roughly the same time, except for one that's way less, then it's like finding a needle in a haystack. But if you can see that, swapping the order of these two things makes the time a bit lower, swapping the order of those two things makes the time a bit lower still, if you have this sort of gradual trajectory where you can see gradually how you can improve your optimization, how you can slowly lower the cost. It's much easier. Visually, think about your cost landscape as an actual landscape. If you have a mountainous landscape, or even just like some rolling hills, it should be easier to sort of navigate towards the lowest point. Whereas if you have an almost entirely flat landscape with a sort of needle-sized hole in the middle, it's going to be very hard to navigate to the bottom of that landscape. So the shape of the cost landscape makes a real difference to how hard or easy it is quantum mechanically, or to classically optimize this quantum cost.
Okay, I see. And yes, it is a complex subject, but I think like at least the basics problem of machine learning, or at least machine learning at its most basic level, or this variational problem, or this minimizing this cost function, I think a lot of it is calculus and linear algebra. I'm sure there are much more difficult and more complex problems, but a lot of these problems involve finding minimum, finding maximum. So a lot of it's calculus, right? A lot of it is basic calculus and finding minimums or gradient descent. So the mathematics behind it, I mean, finding minimums or I don't know if you see it that way, but in machine learning about, for example, a neural network to find the minimal.
It is. But a lot of what we're doing when we're doing quantum machine learning is actually relatively naive, often on the classical side.
Okay.
So once you've computed your cost function on the computer, then you just want to apply an optimization algorithm to try and minimize it.
Okay.
To basically, at each step, tell the quantum computer what parameters to try next.
Okay.
The simplest one is gradient descent.
Okay.
So gradient descent, I think always a good way to picture it is to imagine yourself lost on the top of a mountain in the fog without a map or any idea where you are. And then you're trying to figure out what's going to be your best way of getting down. Well, a decent bet, as long as you don't care about getting down alive, at least, is just following the steepest route down at any moment in time. If you just follow the steepest route down at any moment in time, you should end up at the bottom. Okay. Which is roughly what water does. So actually, if you just sort of find a stream and follow it down, that's going to help you navigate the bottom. So in terms of actually doing this for a cost function, what you do is you measure the gradient at the point you're at.
Okay.
And then you take a step in the direction which is steepest. And that gives you your next point. You then measure the new gradient where you're at and take a step in the direction where it's steepest. So that's one way of doing it. Another way, very, very simple optimization algorithm, is roughly try k different points in different directions, just modify the parameters in different directions, figure out which point is lowest, and then go to that. And then again, make some modifications to try different ways of modifying your problem, so different ways of ordering your delivery houses to be delivered at, see which one's lowest, and then go to that one and just keep on altering. So there are gradient-based methods, and then there were also simpler methods based around basically trying different points in the vicinity and going to the lowest one.
Okay. And I guess one of the common problems, I'm not so sure, but I guess in some cases you can find like a sort of local minimum in the sense that you are right at the point that seems like the lowest. I mean, if you picture like a 3D image, like you will have a point that is the lowest, or in the larger scale, in the global scale, maybe there's another lower point that you miss. So I don't know if I guess also in your work, maybe you encountered this problem, or is this something?
So local minima are a big problem. So if you're doing gradient descent based algorithms, you often want to add a degree of randomness and also play around with the step size to help you jump out of local minima. So if you fall in a local minima, you could imagine that you're stuck there because any other direction is going to be going up, so you're going to want to stay in the same point. But if you add some randomness where with some probability you just jump in a particular direction, that can help you get out. So that's a very classical technique for dealing with local minima. Quantum mechanically, local minima are a problem. There have been some interesting papers pushing out in this direction recently, but it's generally an understudied area. Okay. It's quite hard to quantify when you are going to have lots of local minima and when you're not going to have local minima.
Okay. And I know maybe it's a bit, because you say it's a studied area, so maybe it's a bit speculative, but I don't know, because I mean, in classical, there's a problem to deal with local minimum. Is there a possibility that maybe quantum machine learning or quantum could help in this aspect, or I don't know?
There are some papers that argue that because quantum computers are inherently noisy, so I'm not talking about errors now, I'm talking about shot noise. Okay. So the fact that you only compute observables on average, and if you don't have enough samples, then there's going to be some statistical noise. There's one paper I can think of arguing that if you have this shot noise, this can help actually kick you out to saddle points.
Okay, well.
So if you could otherwise you're going to get stuck in a saddle point, then you've got some noise going to kick you out. That said, shot noise also blurs the landscape. So if your landscape is relatively flat, it makes it harder to figure out which is the cost minimizing direction, because you only get the gradients to a certain precision. And if you don't have them to high enough precision to tell which is the cost minimizing direction, then you're just going to be lost and basically end up doing a random walk. So I am not entirely convinced yet that shot noise really, really does help us to navigate quantum landscapes.
Okay.
But at least in the case of saddle points, in a relatively idealized scenario, there's some evidence they can.
Okay, I see. Okay. And from what I read, I don't know that much, but I think quantum machine learning actually is also, even though it's a new area, it's actually there are quite different approach. That I think people work in quantum machine learning. I know that people use normal machine learning in quantum mechanics to solve quantum mechanics, or there's also the combination of classical machine learning with quantum devices, and there's also all these kind of different combinations. In your view, is there an approach that is the most promising, or I don't know, do you have any hopes for one particularly of these combinations between classical and quantum techniques and devices?
So one important distinction is, I guess in broad terms, quantum machine learning for quantum problems using quantum data versus quantum machine learning for classical problems with classical data. And there are some limited examples that people can cook up showing that quantum machine learning for classical problems with classical data can actually be more powerful than the equivalent classical algorithm. Okay. So they normally work by cooking Shor's algorithm or a modified version of Shor's algorithm into an optimization problem. And then they can show that you can get a quantum advantage, at least for that problem, with this classical data. So that is... But that's for very, very structured classical problems. More generally, it's not clear how quantum machine learning, I think, can help with classical data. It's more obvious how quantum machine learning could help with quantum data, because obviously...
Okay, after some technical problems. Yes, so I think a bit of what you were saying is that it seems you cannot know with 100% certainty, but it seems that quantum machine learning could help there are more possibilities or more probabilities for quantum machine learning to help with quantum data than with classical data, it seems, or like...
Yeah, I mean, it just seems more natural to try and apply quantum machine learning to quantum data.
Okay, I see. And I think with quantum computing, I mean, there's always, we have a lot of hope. It's a super fascinating subject, but I mean, there's also very significant problems. And it seems like, yes, we're advancing, but in your opinion, I mean, for example, just to achieve quantum supremacy, for example, there was an experiment by Google. It was debated. It was not completely sure, I think, if it was really quantum supremacy or not. So I guess a bit the question is, how far do you think, not so far practical applications, because I think that can be still long, but for example, quantum supremacy, do you think this is something that could arrive near, or still a bit far, or I don't know?
I mean, actually, what do you mean by quantum supremacy here? That's the thing.
Okay, I mean,
so it's now been shown, more or less, that randomized benchmarking is not a scalable route to proving quantum supremacy. But could you achieve quantum supremacy with a... I mean, I suspect for a while what we're going to have is a bit of a back and forth. So someone will do an interesting quantum simulation. So I think we're not quite there yet, but maybe in a few years' time, someone will do a 100-qubit quantum simulation on a noisy device and try and claim that it would be very, very hard to do classically. And of course, they might even say that it was impossible to do classically. And that gets everyone excited, and then you have a bunch of groups that then try and work on doing that simulation classically. And yes, they probably find some clever strategies to do that noisy simulation classically, and then the original claim may be refuted, and there'll be a bit of back and forth as people compete. Some people see that as an argument against quantum computing. I almost think it's... this friendly competition between classical and quantum simulation methods, for example, is just advancing our understanding of quantum systems. So whatever, let's just let it roll and let's see what happens.
I notice how sometimes people see as something negative when someone comes up with a classical algorithm that is superior than a quantum algorithm. But I guess we should see it the way you say as something positive in the sense that there is this kind of race, this kind of competition between classical and quantum, and by competing and by trying new approaches, we're advancing and we're learning more about algorithms, about nature, about basically we're making advance on the field by this competition.
Hopefully, yeah, that's sort of the feeling.
Okay, I see. Maybe now I would like to talk a bit more particular about your work. There is one really cool paper that you did. It's called Barren Plateaus Preclude Learning Scramblers. First of all, I find it very cool, and I love the way you present it in the sense that you want you can explain it better than me, I'm sure, but you want to see if with machine learning we can learn these operations, these unitaries that's called scramblers. But I love the way you presented with this hidden Preisser problem with a black hole. So it's so cool that you can deal with these physics problems that combine in a way many areas. It's quantum information, there's a bit of quantum dynamics, and it's I don't know if you would like to present a bit this paper that I found very interesting.
This was a really fun collaboration. So it was with Andy Albrecht, who is a sort of cosmologist by training, with Andrew Swarmborger, who's done a bit of everything.
I was reading because I was in the paper and I was curious, and I actually went into his Google Scholar and I noticed stuff of neuroscience, stuff with physics. It's quite crazy. I don't know this guy, but I'm actually super curious about him because
yeah, exactly. But anyway, this collaboration was meant to be looking a bit at the link between quantum foundations and quantum computing. That's how it started.
Okay.
In the end, actually, and we've presented this result sort of enjoying the link between quantum foundations and quantum computing. We could have presented it completely differently. Had we come at it from a different angle, from a sort of quantum algorithms background, without this collaboration, I think we would have in the end just sold it as you can't learn random unitaries. Mm-hmm. But actually, that's not how we came about it. We were initially thinking about this the Hayden-Preskill thought experiment. So the Hayden-Preskill thought experiment is Alice throws her secret diary into a black hole. Black hole, as nature's fastest scrambler, you would have thought would basically scramble the contents of the diary pretty quickly, making her secrets pretty safe, that no one will be able to decode it. But then actually the Hayden-Preskill thought experiment says that actually, in fact, if Bob shares a maximally entangled state with the black hole, and he knows the unitary dynamics implemented by the black hole, then all he needs to do is collect a few sort of extra photons emitted from the black hole, and he can decode Alice's secret diary. So that's the Hayden-Preskill thought experiment. We were saying, well, how the hell would Bob learn the unitary described in the black hole in the first place? Mm-hmm. So initially this project was going to be, let's investigate whether or not and how Bob could learn the unitary to basically unscramble Alice's diary in order to get her secrets. And then when we started investigating it, we realized, actually, you know what? I think it's not going to be possible. I think nature makes these sort of fundamental restrictions that you can't actually learn scrambling unitaries. Mm-hmm. And so we looked into it further, and we managed to prove a no-go theorem by making links with something known as the Brown-Plateau phenomena. And the Brown-Plateau phenomena is just what I was hinting at earlier, that really the structure of your cost landscape is really, really important in order to enable whether you can minimize a cost function. And what we showed is that if you're trying to variationally use quantum machine learning to try and learn a random unitary, then you're going to invariably end up with this bound plateau cost landscape, where your cost landscape is just incredibly flat in all directions, and it's really, really hard to minimize. So this work, started off as the sort of fun thought experiment, can Bob learn scrambling unitary, and ended up being a sort of fundamental no-go theorem in quantum machine learning.
Yeah, and I find it very cool also because, maybe it's not the first thing that if you don't know about the subject that you will think about with scrambling, but I guess, yes, if there is something, because you present the word as what's the most effective scrambler, so to say, or what's the thing that could scramble the most your system, and of course, a black hole is used as an example as a unitary, a scrambler, I think. Yeah. I find very cool also, and I think that sometimes people see like the fact that you cannot learn this unitary as something negative, but I think it's very important also to know the limits of what we can or what we cannot do, because I mean, at least I'm just a PhD student, but I think sometimes it's difficult to come up with a good problem, or to come with a good also to find like how to tackle a problem. So the fact that there is certain limitations to what you can and what you can do in a certain way, I think like it kind of opens a road in the sense, okay, I don't know exactly how to solve this, but I know these are not the options. So let's search. In a way, you kind of limit the ways to what we can try to search with quantum machine learning, or you will see it differently.
Yes, no, I think this, and I don't really see it as a. I mean, I think I like the link. I think it's fun and cool. I also don't see it as a major problem.
Okay.
In that, generally, we're not going to be interested in applying quantum machine learning to such unstructured problems.
Okay.
Generally, you're interested in applying quantum machine learning to systems with interesting physics, and systems with interesting physics have more structure to them. That's what makes them interesting.
Okay.
So I don't really think this is a fundamental. It is a fundamental limit of quantum machine learning, but rather it tells you to pick your problem sensibly, and the sensible, interesting problems will be ones that have more structure.
Okay, cool. Okay, and I don't know, maybe not for learning scramblers, but because I think there's also a lot of interest from the area of quantum chemistry, and I don't know if you know about because maybe I don't know if it's directly your field, but I don't know if you know about possibilities of using machine learning, or particularly quantum machine learning in quantum chemistry, for example, or what would you say are maybe the most promising roads in terms of application, so to say it, because.
So people are very interested. So this is not really quantum machine learning per se, but more variational quantum algorithms.
Okay.
People are very interested in using variational quantum algorithms for energetic structure calculations.
Okay.
So that is for computing ground states and excited states, and ground state energies and excited state energies of different molecular Hamiltonians.
Okay.
You can then use these to do things like compute reaction rates.
Okay.
So there's a lot of interest in that. One issue is that you need in order to be able to compute interesting chemical phenomena, you need to get it down to chemical precision. And that is hard to do on a quantum computer because you need lots and lots of shots to have high precision. So I think it's often argued that at least in the near term, material science and condensed matter will see applications of quantum algorithms sooner because you don't have quite the same high accuracy requirements in those contexts.
Okay, I see. Okay. Maybe a bit to finance, is there one particular project in which you're interested at the moment, or maybe a current project that you're working that you would like to share with us, or something that interests you the most at the moment?
Okay, so if you want something interdisciplinary, maybe I can talk about the follow-up project to the Scramblers project.
Okay, I would like to hear about this.
So this is again the same team. So we've got Andrew and we've got Andy. We've now also got Arsalan, who is a PhD student of Andy's. And we've got my student Manuel on it. And the aim of this is to try and propose a variational quantum algorithm to understand what is a subsystem and what are approximately classical subsystems, and what are something called pointer states. So the idea being is like, as big, hot, macroscopic objects, we're very good at identifying other big, hot, macroscopic objects. I can identify this system as a subsystem and this bottle as a subsystem, and these things are relatively well-defined objects that we can describe as interacting. And even at the micro scale, typically when we write down a Hamiltonian, we take, 2 electrons and we describe how they interact. What if I just give you a random Hamiltonian? The question is, given this random Hamiltonian, can you describe this? Is there a way of looking at this Hamiltonian as pertaining to approximately well-defined subsystems? So you just have the energy spectrum. And you want to know whether there's a story you can say about that Hamiltonian corresponding to different subsystems that are approximately non-interacting. So it's sort of really taking a step back from our big anthropomorphic perspective of look, there are all these objects around us, let's try and describe them. It's like, take this random Hamiltonian, can we come up with a story in terms of subsystems? And then, so that's sort of the raw question. And then the question is, can quantum computers help us to find these descriptions? So if you just take as your input a Hamiltonian, can we come up with an algorithm to say whether or not that Hamiltonian can be described in terms of these approximately well-defined subsystems?
Okay, well, okay, no, but it sounds very cool. And I think sometimes people, they focus maybe, yes, I understand that applications are very important, but I think it's also important just to explore new ideas and to be creative. And I think like, I don't know how is it for you, but I think like as a scientist, maybe what inspires you the most is most like interesting ideas, creativity. And of course, I mean, it's very great when applications comes, but I think, I don't know how is it for you in the sense that how you approach problems instead that you look specifically for application or you just want to explore ideas. I don't know.
I think it's always what's fun.
Okay.
I think in the end, it's great when there's an application. I think it makes it more fun when there's an application, but so often the best part of a project often isn't the result. Oh, this is so cliche, but sort of the journey to get there. So at the moment, another project, we're looking at generative modeling. So we're looking at quantum generative modeling. So this is trying to learn, so ChatGPT, for example, is basically a generative model. So you feed in training data and then you want to be able to generate more samples from that. So give a generative model lots of pictures of cats and you want it to be able to spit out new pictures of cats. So people have been looking at quantum generative models. So feed in lots of quantum cats and get it to spit out more quantum cats, roughly, naively. Don't take that too seriously. And then you can look at like the trainability of these quantum generative models. So what do their cost landscapes look like? And actually what we've got our teeth into is we've decided that there are two different types of cost functions you can use for this. Something that we want to call explicit and something we want to call implicit.
Okay.
And actually pinning down this distinction is really, really hard. And we've spent weeks arguing over it. No one who reads this paper is really going to care that much, but we really want to get this distinction right.
Okay.
And we've just been enjoying arguing about it. We want to get it right, and it's just a really fun puzzle. And so that's actually at the moment what's probably exciting us most.
Okay.
I mean, in the end, the wider community is going to be more interested in the results about what cost function they should and shouldn't use. But this little detail is the one that we found fun.
Okay, so cool. Okay, and maybe it's not something directly your field, but I'm curious about knowing your opinion. Machine learning is clearly advancing along, especially right now. Machine learning, it seems like, it was already big, but it seems like right now it's getting almost scary important. So I don't know, a bit like, what is your opinion in the sense like, for example, you mentioned ChatGPT. How do you think it's going to influence not only physics but our lives? I guess in a sense that it seems like I don't want to be like create too much hype or be paranoid, but it seems like it's a big thing. I don't know. What's your opinion?
I'm actively telling students to use it.
Okay.
I'm saying why. Yeah, so this paper we just written, we've used ChatGPT to write the abstract.
Okay. Wow.
we've edited it, we've tied it up a bit, but first draft of the abstract, ChatGPT.
Okay. Wow. Okay.
This was because it was a paper on generative modeling. It's now obvious on a paper on generative modeling to try and use some generative modeling to write it, but as a tool, we've also used it to. We used it at one point to look up a proof for a small probabilistic theorem that was going to help a wider proof, and it gave us a proof for that. I think we should embrace it as a useful tool.
Okay. Yeah, I guess sometimes people, I understand why there's a certain kind of, not scare, but in a sense like it's too much change is something like very big, I think. So obviously there's going to be a certain, not necessarily negative scare, but it's a bit like, okay, there's a lot of change, but I guess like there's also clearly so many positive aspects. And yes, there are jobs that are going to be replaced. That seems like a fact, but there are also new jobs that are going to be created that maybe are more related to creativity and they're maybe related. So
we can save ourselves some time to do more interesting things.
Okay, well, so yes, it seems like, I think in pretty much every area, but as you say that in physics, it seems like it is already a great tool.
I think it's I don't think it's going to help us for the really interesting stuff. It can't figure out the distinction between an explicit and an implicit cost for us. That we need to pin down ourselves. It's not going to be able to do that sort of careful conceptual analysis. But to do bog standard mechanical, I don't know, writing a letter to an editor. Or there's so much stuff we do that is really generic, that is just effectively copy and paste and edit. To be honest, it's still not quite there yet.
Okay.
We did try and use it to help us write a paper submission letter to an editor. And what it wrote was too generic. But I think soon it will figure out how to do this kind of thing, and that can just save us some time.
Okay. And I don't know, not necessarily a physics student, but maybe, what would you say, like an advice for like let's say the activities or the things that one should try to focus on learning? Because I mean, a lot of things going to be replaced, but there's going to be maybe some other techniques or abilities that maybe it's not so easy to replace. So I don't know, maybe someone who just beginning his physics career, what he or she should focus, or I don't know whether it's sort of like the abilities that one should focus to learn, or I don't know.
I mean, I think if you've got good courses, if you have good courses, your lecturers will give you questions that can't be solved by ChatGPT. And it's those questions that will be interesting and exciting and train you to do the type of research that you want to do in the future. Like ChatGPT and other generative models, all they do is regurgitate stuff that they've already seen. And yeah, some of the work we do is regurgitation. Coding, for example. Some bits of basic code, it's apparently, I've not used it myself like this yet, but I'm quite excited to try it. It's great at. But whenever you're doing something original and different that actually requires some thought that hasn't been done by however many humans before, it can't help you with that.
Okay. Yeah. Yeah, and I guess like also with creativity, yes, maybe I don't know, maybe I'm being too naive or in a way, but I think there's a certain human element that is quite unique. I don't know, for example, let's say if ChatGPT can do a song, I don't know, for me it's not the same that when I know an artist and I know his life or her life and its struggle, and there's certain kind of, I don't know if it's a bit romanticized this thing, but I think there's a certain human aspect that, I mean, we don't really know, but like I think that for us as humans, it's special. And even like if a computer can do something, there's still like some human element to it. I don't know. Yeah. But I don't know. For example, like, do you see yourself if ChatGPT makes a song or or some piece of artwork? Will you appreciate the same in the same way that any of your favorite artists or something like this, or not really? Or
No. Okay, I guess I was pushing back up against your claim that there wasn't a human element to it. In that, to some extent, there is, in that it's 20,000 human elements to it, in that it's feeding on everything humans have done in the past. So there is a human element to it. You've also got the human feeding in the prompts. So you've got the human saying, can you make it a little less sad? But fundamentally, it's not going to be very original.
Okay.
And if everyone just henceforth does everything using ChatGPT, we're just going to be regurgitating the same stuff, recycling it, reincarnating it, and nothing new will ever appear.
Okay, yes. Okay, yes. Again, I'm not an expert. I was reading something about like because yes, there's new data that's gonna come, but a lot of this new data is gonna come from ChatGPT. So in a sense, it's gonna start learning from data that already is sort of like contaminated, so to say. Yeah. So in a way that what I'm saying is like or not contaminated data is gonna become more valuable, or I don't know.
It's not contaminated. It's just not going to be new.
Yeah,
it's just,
I guess that's a better term. Yeah. Okay, so yes, no, nothing. I just want to say that first of all, thank you for accepting. I know that you gave a talk, and it was again, quantum physics congress can be very interesting, but I think there also can be exhausting. So thank you so much. Yes, I don't know. Thank you. I find your work very interesting, and yes, maybe I don't know. Maybe some advice for physics students that you want to say, or I don't know, like that you want to share for someone who's starting a career or who wants to start in the area of quantum science. Maybe is this a particular advice that you would like to give, or
just have fun.
Okay.
Personally, weird one. I did philosophy and physics as an undergraduate, and I found the philosophy of physics I did really, really helpful.
Okay.
Like having to. So, for example, this sort of debate about how to define loss functions, or how to pin down concepts. Really good training for that was my undergraduate in philosophy of physics. So, if you like foundations,
and you feel guilty thinking about quantum foundations because you think it's not relevant to your problem sheets, don't worry, it will come in useful later.
Okay. Actually, to the previous guest, I always ask something related to the foundations of quantum physics or the problem of, I don't know, is there a problem with fundamental quantum mechanics? And I stopped making the question because, seriously, every quantum scientist say me that they don't think there's a problem, and no one seems to have philosophical problems with quantum mechanics.
Oh, for God's sake. I mean, the measurement problem is a fundamental problem. It's like absolutely baffling. And it never gets any less baffling. You just learn to not think about it.
Okay, but it's seriously, like I asked the three previous guests I asked, and no one seems to have a problem.
There's not.
The thing, like, apparently it seems like whatever problem this is, you can do your work. Because, I mean, I think these are really good scientists. I think they're really good quantum. I do think they understand their work and stuff. But, so yes, maybe I will ask you that. Is there a problem? Is not there a problem? Why some physicists, very renowned physicists don't have a problem? Why others yes? I don't know.
So I think it's not widely taught enough, the measurement problem.
Mm-hmm.
I only was taught it as part of my philosophy of physics course. We didn't cover it in the physics course.
Okay.
It's all based around the concept of measurement and whether or not the concept of measurement is well defined enough to appear in a fundamental theorem. So textbook quantum mechanics, we're told that quantum states evolve unitarily until they're measured. And then suddenly we have this collapse of the wave function, and they evolve non-unitarily. But measurement devices are also quantum objects, and quantum objects evolve unitarily. So there's a contradiction there. And in practice, we can ignore this most of the time. Most of the time, there is a relatively clear distinction between approximately classical measurement device and our quantum system. Okay. So when we're actually doing our research, we can ignore this problem. But when you try and think about the fundamentals of what quantum mechanics actually means, we can't ignore this problem.
Okay.
And in my view, the most natural resolution is there is no collapse. Everything is unitary. And when you start to think that, you are very naturally led down the road of many worlds.
Okay.
And the most natural, consistent interpretation of quantum mechanics without modifying it is many worlds. And then that's obviously clearly baffling and crazy.
Okay.
So then you just forget about it and get on with your everyday life doing calculations because it's a bit too much to handle.
Okay, well, I think it's a serious thing. Like, a lot of physicists work in this many words interpretation, but I think you're the first physicist that I know who take this very seriously, in a sense that, yes, in a sense, you're a proponent, or is your favorite.
I don't necessarily. I'm not sure I believe in it. Okay. I don't know what I think.
Yeah, but you don't see it as a crackpot. You don't see it as crackpot.
No. I think it's if you just intake quantum mechanics at face value, that's what you end up with.
Okay.
And then obviously it's crazy, but it's also what you end up with if you take quantum mechanics at face value, and quantum mechanics at face value quantum mechanics is incredibly well verified. It's been used to make novel, unexpected predictions that are then being verified by experiments. It's one of the most accurate theories we have, up to caveats about consistency with gravity. So if this theory at face value implies many worlds, it's something that we should think about and see whether we can understand. And I'm not sure whether that is the right interpretation. I don't know whether the hope is maybe we will one day come along and find some modification of quantum mechanics that somehow does away with the measurement problem. But I do think it's a serious interpretation that requires thinking about, even if we eventually decide that it's wrong.
Okay. I guess one of the counter arguments will be that, from what I read, it seems like some scientists find it as scientific, in the sense that if there is not a way to experimentally prove these many words, it seems like for some it could not be actually called science. So I don't know if this is a problem for you, or do you find it problematic? I guess it is problematic at the very least, or not for me.
It's tricky because I still maintain that it is. So if you have we have evidence for superpositions at the microscopic scale,
Okay.
and we have no evidence for dynamical collapse.
Okay.
That these superpositions are actually broken down as you go to a macroscopic scale. And given we don't have evidence for that,
Okay.
it would seem that you effectively have many worlds. I need to think about it further. I don't really see it as ascientific.
Okay. Okay.
The more fundamental problems is understanding probability in many worlds.
Okay. I guess something related to normalization, maybe, or
Like how you get out the Born rule, how you to understand probability in a universe where you end up with a superposition of everything.
Okay.
I find that a more fundamental problem.
Okay.
But I don't fully understand the claim that it's ascientific, because it's more. Okay, I find it more ascientific to try and do something like, say, measurement special.
What is measurement special?
That say that you have a collapse postulate.
Okay. Okay.
That somehow measurements are different. Unless you have evidence for it. If you can find evidence of dynamical collapse, fine. But there are some of these weird sort of quantum relativism approaches that I really, really, really don't understand. I cannot get my head around them. They say they're Copenhagen done well, but I find them absolutely baffling because they seem to rely on some fundamental distinction between a quantum system and a quantum observer, or a quantum system and a quantum measurement. And that to me seems ascientific, because there fundamentally isn't that distinction. Okay.
Yeah, maybe for people who are not that familiar, at least with me, I think with most students, is that when you enter like a university level quantum mechanics course, one of the first things that you encounter is these postulates, right? Like they say, okay, so if you measure, you make a measurement. It's not exactly defined what is a measurement, but if you make a measurement and your wave function collapse, and it's something that happens, but it's not. I mean, it's not something that it was like sort of like analytically derived, or that there is like really a convincing explanation of why it is that way. We just know that it happens, or like at least that's one of according to this interpretation of Copenhagen. It seems like this is something that happens when we observe.
When does it happen? Is the point. When does something cease to evolve unitarily and suddenly obey this collapse postulate? Like, that's not well defined.
Yeah. I also was reading because I mean there is some people relate the phrase by Einstein, I think, about like spooky effects by entanglement. But I was reading another view that apparently some scientists was reading that it was malinterpreted in the sense that Einstein referred more to the fact that if you have like a sort of like a wave function in superposition, how did it happen to be, I don't know, to have like this wave function is sparse, or to have many options? How did it pass from the fact to be in superposition to actually acquire one definitive value? So apparently he had also a lot of problems with this view of quantum mechanics, but I don't know, like, yes. Okay, so well, at least we can say that there is a philosophical problem with quantum mechanics. The measurement problem there is according to view, but which is strange because I mean the truth is also you can do quantum research on quantum physics without not necessarily getting involved with this problem.
The point is, in practice, we have decoherence, and in practice, moderately large measurements end up basically decohering in the position basis. And so in practice, we have a relatively clear notion of the distinction between a quantum system and a measurement device.
Okay.
And that means in practice, we can ignore these issues. Okay. But that doesn't stop there being a fundamental issue that actually the notion of a measurement is ill-defined.
Okay. Okay, I have to think about this. Okay, yes. But yeah, I find this subject very interesting. It's also, in a way, difficult because I think it's very hard. I don't want to say impossible, but it's very difficult to come up with experiments, or I think so far no one has come up with an experiment. I don't know if it's possible to come up with an experiment to sort of like distinguish between different interpretations. So I guess this will be one of the major problems. So I don't know, experimental evidence, will you?
So dynamical collapse is nice and scientific.
Okay.
The idea that actually there is some non-linearity that kicks in at a certain length scale, and people have done experiments looking for that. And the point is they don't find anything.
Okay.
So that one at least is testable. The rest, trying to distinguish between many worlds, Bohmian mechanics, and something like quantum relativism. I don't know whether there can be experiments done.
Okay. But I mean, yes, I mean, one could never know. For example, I mean, one of the greatest results in quantum mechanics, I think, or one of the greatest advances, at least in fundamental quantum mechanics, was because of the Bell inequalities. So, I mean, it's not easy. I don't know if it's possible, but there are certain ways of tackle some fundamental problems in quantum mechanics, I believe so. I mean, we don't really know, but like you cannot, I guess it will be not convenient to give up and say, oh, no, we can, but rather like keep searching and try to find out, but I don't know.
Yeah, though I think the game there is often about just at the level of foundations, it's can you formulate a consistent theory. So my impression, it seems to me that quantum relativism just isn't consistent.
Okay.
Many worlds, despite being crazy, is at least consistent up to maybe some caveats about how you understand probability.
Okay.
And then Bohmian mechanics, I think that is also consistent. But the argument against that one is it posits the existence of these sort of postulates. It has these like I can't remember what they even call them. It's got these like little particles that have their own trajectories. And I think, as far as I understand, that is a consistent theory, but then you can just kind of apply Occam's razor to it and say, what's the point in adding these empirically inaccessible particles? Now, of course, you could say the same to many worlds. What's the point in positing these extra worlds?
Mm-hmm.
But at least these extra worlds don't require adding anything to the theory. Whereas Bohmian mechanics, you have to posit the existence of these point-like particles and these trajectories. So you actually are adding something to the theory. Okay. So by Occam's razor, you almost seem to end up with many worlds, unless you're someone that then tries to apply Occam's razor to many worlds, objecting to, I don't know, it's those kind of arguments rather than experiments, it seems.
Okay, I see.
It's arguments about consistency, whether the theories are consistent and whether they, which one works best with Occam's razor.
Okay, so yes, I have to think about this. But yeah, honestly, it's very refreshing to have a different opinion to someone that's saying that you don't care or something. Because sometimes I get those kind of answers. Sometimes people don't care, which I don't judge. I don't know. I want to just clarify that I think these are very good scientists. I think these are very good scientists.
Well, get someone who works in philosophy of physics. They would all be turning in their graves with my attempts to describe the different theories right now, sort of dredging out old memories from studying them. But yeah, if you want to talk to someone about quantum foundations, get someone working on quantum foundations, you'll definitely get people to engage them.
Okay, cool. So yeah, honestly, thank you very much again. And yeah, it was very nice. Thank you very much.
Thanks for having me.